speak about the AI search algorithms. The first one I'll start with is hill climbing. Hill climbing is a local search algorithm that incrementally improves solutions by selecting the best next step. This algorithm actually starts with the current state and keeps on iterating, each time making a better improvement, and in such a way it operates under the best immediate option and finds a solution depending on the current situation or the current sample space. So one of the practical examples is optimizing traffic light in urban management areas. It starts with the current state of the traffic and keeps on iterating up to when there is no traffic jam. But one of the challenges is that it, it can get stuck in local optima or plateaus, preventing further improvement. Then the second one is simulated annealing. Simulated annealing mimics the physical process of annealing where materials are heated and cooled to optimize their structure. This algorithm uh, it accepts worse solutions initially, but as it keeps on iterating, it keeps the probability of it allowing a worse solution keeps on reducing, and in such a way, it it escapes local optima, unlike hill climbing. So one example is that in the public housing allocation, you can accept worse solutions. That is meaning you can allocate housing to worse areas and also allocate some to best areas, therefore bringing about a balanced solution of houses. So one of the key characteristics is that it effectively balances exploration of the solution space, as I've explained it. Even undeservedly, I mean, even poorly developed areas will get some housing. So the third one is the genetic algorithm. This is inspired by the principles of natural selection as seen from the word genetics, and it operates by evolving solutions through mechanisms. Here, the fitter individuals of that current generation are the ones that give the the children of the next generation. Then the fittest individuals of that next generation are the ones that give the children of the next generation, and that continues. The key characteristics include these algorithms utilize population of potential solutions, subjecting them to evolutionary processes, as I have explained. The fittest individuals give rise to the next generation. So one example is that they are used in optimizing resource distribution in public health centers. This is like when some doctors are actually assigned to areas that they are not deserved to be in. So they are particularly well suited for handling large solution spaces and avoiding local optima, unlike hill climbing that usually gets stuck in local optima. Then, how responsible and explainable AI can explain this? For responsible AI, this actually deals with the ethics and the fairness of the algorithm design. Take, for example, if we are prioritizing healthcare resources for undeserved communities, then simulated annealing is actually approved by responsible AI since it ensures critical need to receive the attention and care they deserve. Yeah, so for explainable AI, this mainly deals with transparency or how we can explain it to human beings so that they gain our trust. How the AI can be explained to human beings to gain their trust. For example, how we can describe how hill climbing can improve traffic signals and therefore building public trust and acceptance. Then we move on to adversarial search. Adversarial search just involves optimizing outcomes while simultaneously minimizing the success of the opponent. Yeah, and it is actually a, a strategic. It is strategic in reasoning in competitive environments. Take for example in legal disputes, we have a lawyer and he has a client. This lawyer is actually aiming to improve the success of the client, whereas minimizing the success of the no is aiming at improving the success of his client, whereas minimizing the success of the other party. So it's like he wants the client to win and he wants the other party to lose. Yeah. So the other the other example is in business negotiations. When you're negotiating, you're aiming at making more profit at the expense of the other party losing. So that is also called adversarial search. So one of the importances is that it's fundamental for developing competitive strategies, and it is widely used in fields like game theories, uh, AI, AI and robotics, and creating a rich area for exploration. Yeah, so Minimax algorithm, this is under adversarial search or examples of algorithms under adversarial search. The Minimax algorithm is a recursive technique in two-player games. These are games where one player's game is the other player's loss. So it ends at maximizing the chances of player one, who is the maximizing, who is the maximizer, whereas minimizing the chances of success of player one, who is the minimizer. Actually, to break it down, the player X, who is the maximizer, wants the best move, whereas the player Y wants a move which counter attacks the best move of the player one, thereby reducing on his chances of success or even creating a draw. Yeah, so the algorithm focuses on strategic interplay between competing players, ensuring decision making reflects the optimal outcome, as I have explained it. Then the expect min max algorithm. This is an extension of the min max algorithm, only that this one includes randomness. Hmm? It is not like in Minimax where it is not random. Take for example in Monopoly, it is you have decisions. Let us say player X is the maximizer. He has several decisions, but those decisions are determined by the dice rolls that he or she gets. So the algorithm calculates optimal moves by integrating the uncertainty of the game's outcomes. So player Y, the minimizer, is actually looking for either a draw or is reducing the success of player X, who is the maximizer. But this is all done within randomness. Like for example, the dice roll for the Monopoly game. So the key feature is that this algorithm introduces chance nodes and expected value calculation. That is the dice rolls. If you get 2 plus 6, so meaning you can move one of you can move up to the eighth decision, or somewhere you can move the 6, then you move the 2, just like how that game is played. They they both, as you can see here, they're highly effective in games that involve both strategy and randomness. Yeah. So the alpha beta pruning, this is just a technique for optimizing the minimal algorithm, and it is that it is so in okay, it is done in such a way that the best it represents the best choice for the maximizing player, while beta represents the best for minimizing the player's significant reducing space. So alpha is the best decision of player X, who is the maximizer. Then beta is the best decision of player Y, who is the minimizer. So now in this alpha beta pruning, we will remove the nodes which won't directly affect the success. Like like take for example in chess, this technique allows players to skip evaluating moves that do not lead to better outcomes, thereby streamlining the decision making process and reducing on the time. Yeah, because it eliminates the nodes which don't actually affect the final decision. Yeah, so now if we move on to adversarial machine learning, uh, adversarial machine learning actually focuses on creating robust models that can withstand attacks from adversarial examples like the ones we discussed, where adversaries aim to deceive and they aim to mislead the machine learning systems. Take, for example, we have attackers and we have defenders. Attackers aim to mislead the system, whereas these defenders try to reduce on the impact or the success of the defender, of the attackers who are on the system, who want to attack the system. So common applications include fraud detection and image recognition, where algorithms must differentiate between legitimate data and deceptive data. So the primary objective is to develop a robust model. Okay, let me continue from where I stopped from. I was speaking about the adversarial machine learning. The primary objective is to develop models that not only defend against adversarial attacks but also maintain accuracy and fairness in predictions. So, the differences between uh, the adversarial search and adversarial machine learning, the similarity, they are somehow similar, but again, there's some difference. Like the similarity, we could say both fields involve strategic reasoning against opponents. This one opponent has to counterattack the other one who wants to win. So you must reason and you must plan your steps. Yeah, focusing, as you can see, you're focusing on anticipating behaviors, optimize responses in competitive scenarios. Then the difference is that adversarial search typically operates in deterministic environments. Take for example the monopoly. We are throwing the dice. So the dice is the one which actually determines your decision. Whereas with adversarial machine learning, this is dynamic and uncertain and actually harsh environment. Because the attacker of your system, you don't know the steps he or she wants to use. You can use steps that you never even thought they would actually use. So that is the difference. And then the key point is that the primary the primary aim in both approaches is to outmaneuver adversaries effectively, where in games or machine learning context. So I think that is the end of my slides. I mean, that's the end of my presentation. Thank you for your time.